Hello there. Welcome to Lecture 17, Phase Change. This lecture expands on our understanding of heat and thermodynamics by discussing the states of matter and how substances change their phase. We'll learn about the heat energy required to create phase changes and analyze the heat, temperature, and phase diagrams of different substances. Each of the following concepts will be discussed in this video: phases of matter, evaporation and condensation, boiling, latent heat of vaporization, melting and freezing, latent heat of fusion, the triple point, sublimation and deposition, ionization and de-ionization, and phase change diagrams. In our everyday lives, we experience 4 states of matter: solid, liquid, gas, and plasma. A solid is a material where the molecules or atoms are very tightly bound together. This gives a solid a very rigid volume and shape. If I move a rock around, it is not going to change its shape or its size at all. A liquid is a material where the molecules or atoms are free to move about, much easier than in a solid. However, the molecules are still packed rather close together. A liquid will change its shape, but cannot be easily compressed to change its volume. When I pour this liquid from a cylindrical beaker into another, you can see that the shape of the liquid changes as it pours. However, the same amount of liquid is present, even as the shape changes. In a gas, the molecules are very free to move about, and they are not arranged tightly at all. This means that the shape and volume of a gas is free to change. A gas will assume the same shape as the container that it's in, and it can be compressed to take up less space or expanded to take up more space. If you've ever used an air compressor to fill up your car or bicycle tires, then you've changed the volume of air. Unfortunately, it's not something I can demonstrate as easily as with a rock or water. A plasma is an ionized gas. That is to say, it's a gas with so much energy that electrons have been ripped away from the atoms. While this might seem like an exotic state of matter, it's something we experience in our daily lives. Stars, including our sun, are made out of ionized hydrogen and helium, plasma. Lightning is a plasma. Even fluorescent bulbs use plasma to create light. In general, we can characterize each state of matter by the amount of energy it has. A solid has the least amount of energy, followed by a liquid, followed by a gas, and then plasma, which has the most energy. Phase changes describe how a substance can be converted from one phase to another. When a substance goes from a solid to liquid form, that is called melting. From liquid to solid form, that is called freezing. The phase change from liquid to gas is called evaporation. From gas to liquid is called condensation. From a gas to plasma is called ionization, and from plasma to gas is called de-ionization. Some materials are able to convert directly from solid to gas, which is known as sublimation. The conversion from a gas directly to a solid is known as deposition. We will discuss each of these phase changes in more detail throughout this lecture. While I mentioned that there are 4 common states of matter, there are in fact a lot of other states of matter. However, they tend to be very exotic. That means they need to be under very special situations to occur. Some states of matter require temperatures very close to absolute zero or require extraordinarily high pressure to exist. We are very unlikely to ever deal with these states of matter in our lives. Evaporation is the phase change that occurs when a substance converts from a liquid to a gas. Because a gas has more energy than a liquid, that means that energy must be provided to a substance to get it to change its phase. The exact amount of energy required will be discussed in a few moments when we talk about latent heat of vaporization. In the evaporation process, molecules in their liquid state absorb energy. That energy loosens the bonds between the molecules, freeing them to move about as a gas. Heat is required to convert a liquid to a gas. That heat must come from somewhere. When evaporation occurs, the surrounding environment cools down after it provides that heat. Evaporative cooling is something that we as humans experience frequently. Our bodies sweat when it's warm. Our skin provides the heat required for that sweat to evaporate, causing our skin to cool down. Evaporative cooling can also be used in homes in areas with a dry climate. In the Chicagoland area, evaporative cooling is not as effective as air conditioning due to our humid summer climate. To demonstrate that evaporation is a cooling process, I dipped a thermometer in a bottle of alcohol and then waved it around in the air to get the alcohol to evaporate. Heat from the thermometer changes the phase of the alcohol from a liquid to a gas, and as a result, the temperature recorded by the thermometer decreases. As mentioned, this is the same cooling process that we experience when we perspire. The drinking bird is another example of the cooling properties of evaporation. The bird's head is dipped into water. As the water evaporates from the bird's head, the cooler temperature causes the pressure inside the head to decrease, as we discussed in Lecture 14. This pressure differential causes the fluid inside the bird's body to be drawn up into the head, causing a net torque. As we learned in Lecture 8, a net torque will cause rotational acceleration. The bird dips its beak, and the fluid in the head is able to travel back into the bottom of the bird. This process repeats until the bird's head dries off and evaporation stops. Condensation is the opposite of evaporation. It is the phase change from a gas to a liquid. As the molecules lose energy in the condensation process, they start to move in more structured bonds, which gives liquid a more well-defined arrangement than gases. The energy lost by the substance is released into the surroundings, causing them to warm up. Condensation is something you may have noticed if you have a cold glass of water or can of soda sitting out on a warm or hot day. The water vapor in the air surrounding the container will condense into a liquid form. It is important to note that, for a given substance, evaporation and condensation occur at the same temperature. Water will evaporate at 100 degrees C, and it will also condense at 100 degrees C. Whether it converts from a liquid to a gas, or from a gas to a liquid, depends on whether or not it is gaining or losing energy at this temperature. We just finished discussing evaporation, the change of state from liquid to gas. Perhaps you have also heard the term boiling, which also describes the change of state from a liquid to a gas. Evaporation is a surface phenomenon. That is, even if we have a large volume of liquid, evaporation only occurs at the interface between the liquid and the surrounding fluid, such as air. For example, I sprayed a small amount of alcohol onto a lab bench and placed a fan nearby. The alcohol evaporates by changing phase to a gas at the surface. The pool of liquid becomes shallower and shallower until all of the alcohol is converted into a gas. Boiling is a volume phenomenon. It occurs when the gaseous form of the substance, which we might call bubbles, are able to form without being squashed out of existence by atmospheric pressure. In this video, I use a hot plate to boil water. You can see that the water turns into a gas within the liquid, and then those gas bubbles move upward due to a buoyant force and then leave the beaker. Boiling has to do with atmospheric pressure. At standard atmospheric pressure and temperatures, a beaker of water is not going to boil. This is because any gas bubbles that form will be collapsed due to the pressure of the atmosphere pushing down from above. As the liquid heats up, the energy of the bubbles increases until a certain point where the bubbles overcome atmospheric pressure. This is known as the boiling point. If you move to a higher altitude, the atmospheric pressure is lower. This means that less heat is required to boil water. In fact, if you have ever cooked cake or brownies from a mix, you may see a high altitude note on the box. This is because water boils at a lower temperature at high altitudes, and things may not cook the same way as they would at sea level. It is possible to boil water at room temperature by reducing atmospheric pressure. In a classroom, I can do this with a vacuum chamber. By pumping out most of the surrounding air, there is no longer enough pressure to collapse any bubbles that form in the water. This beaker of water is boiling at room temperature. This demonstration emphasizes why humans need to wear pressure suits at extremely high altitude in flight or in the vacuum of space. Above about 19,000 meters, the fluid in our throat and lungs will boil away. A pressure suit compensates for this by compressing the human body, preventing this boiling process. Latent heat of vaporization describes the amount of heat required to convert 1 gram of a substance from a liquid form to a gaseous form. Alternatively, it defines the amount of heat that must be removed from 1 gram of a substance to convert it from a gas to a liquid. During the evaporation or condensation process, it is important to note that the temperature of the substance remains constant. Any heat entering the liquid does not increase the temperature. It changes the molecular arrangement of the atoms. Any heat leaving the substance does not change the temperature. It changes the arrangement of the atoms. As mentioned, because the evaporation and condensation temperatures are the same, and the amount of latent heat is the same for both processes, we can only tell if a material is evaporating or condensing by determining if the object is gaining heat or losing heat. If the substance is gaining heat, then the molecules are being reconfigured into a gas and evaporation is occurring. If the substance is losing heat, then the molecules are being reconfigured into a liquid and condensation is occurring. Water has a relatively high latent heat of vaporization, especially compared to other common substances. The latent heat of vaporization of water is 540 calories per gram. This means that 540 calories of heat must be added to 1 gram of water at 100 degrees Celsius to convert it into 1 gram of steam. The equation we can use for calculating the amount of heat required to change the phase of a substance from liquid to gas is Q equals m times LH. Heat equals the mass times the latent heat of vaporization. To convert 5 grams of water from a liquid to a gas, we would need to multiply the mass, 5 grams, times the latent heat of vaporization, 540 calories per gram. The result is 2,700 calories. Acetone has a latent heat of vaporization of 124 calories per gram. If we wanted to convert 48 grams of acetone from a liquid to a gas, it would require 5,952 calories of heat. Conversely, to convert 48 grams of acetone from a gas to a liquid, we would have to remove 5,952 calories of heat from the substance. Melting is the phase change that occurs when a substance converts from a solid to a liquid. Because a liquid has more energy than a solid, that means that energy must be provided to the substance to get it to change its phase. The exact amount of energy required will be discussed in a few moments when we discuss latent heat of fusion. In the melting process, molecules in their solid state absorb energy. That energy loosens the tight bonds between the molecules, allowing them to move about more freely. Heat is required to convert a solid to a liquid. That heat must come from somewhere. When melting occurs, the surrounding environment cools down after it provides that heat. Freezing is the opposite of melting. It is the phase change from a liquid to a solid. As the molecules lose energy in the freezing process, they start to form tight bonds, which gives solid a very well-defined shape. This energy lost by the substance is released into the surroundings, causing them to warm up. It is important to note that, for a given substance, melting and freezing occur at the same temperature. Water will freeze at 0 degrees C, and it will also melt at 0 degrees C. Whether it converts from a solid to a liquid, or from a liquid to a solid, depends on whether or not it is gaining or losing energy at this temperature. In the winter, salt is frequently placed on roadways and sidewalks to cause ice to melt. Salt will block the bonds between water molecules, making it much harder for liquid water to freeze into a solid. This lowers the freezing point. Salt water has a lower freezing point than fresh water. If the freezing point is lower, the melting point is also lower. Frozen salt water will melt at a lower temperature than fresh water. Latent heat of fusion describes the amount of heat required to convert 1 gram of a substance from a solid to a liquid. Alternatively, it defines the amount of heat that must be removed from 1 gram of a substance to convert it from a liquid to a gas. During the melting or freezing process, it is important to note that the temperature of the substance remains constant. Any heat entering the solid does not increase the temperature. It changes the molecular arrangement of the atoms. Any heat leaving the liquid does not decrease the temperature. It changes the molecular arrangement of the atoms. As mentioned, because the melting and freezing temperatures are the same, and the amount of latent heat is the same for both processes, we can only tell if a material is melting or freezing by determining if the object is gaining heat or losing heat. If the substance is gaining heat, then the molecules are being reconfigured into a liquid and melting is occurring. If the substance is losing heat, then the molecules are being reconfigured into a solid and freezing is occurring. The latent heat of fusion of water is 80 calories per gram. This means that 80 calories of heat must be added to 1 gram of ice at 0 degrees C to convert it into 1 gram of water. The equation we can use for calculating the amount of heat required to change the phase of a substance from a solid to a liquid or from a liquid to a solid is Q equals M times LH. This is the same equation as before, but now, instead of using the latent heat of vaporization, we use the latent heat of fusion. To convert 47 grams of water from a solid to a liquid, we would need to multiply the mass, 47 grams, times the latent heat of fusion, 80 calories per gram. The result is 3,760 calories. The triple point is a particular combination of temperature and pressure at which a substance will exist in liquid, solid, and gaseous form simultaneously. This might seem outrageous, but it is simply an incredibly cool property of matter. When held at the triple point, both the freezing melting and condensation evaporation processes can be seen happening at the same time. Unfortunately, the vacuum pump I use to boil water at room temperature does not quite get to a low enough pressure to demonstrate the triple point of water. However, I have video links on my physics website that you can take a look at to see the process in action. Watching a substance freeze and boil at the same time is amazing. Sublimation is the process by which a substance goes directly from a solid to a gas without going through the liquid phase. Some substances, such as carbon dioxide, cannot exist as a liquid at standard atmospheric pressure. This video shows a piece of dry ice as it was recorded over a span of half an hour. While you cannot actually see the carbon dioxide when it turns into a gas, it is clear that the piece of dry ice becomes physically smaller over time, and no liquid is generated. The carbon dioxide goes directly from the solid to gaseous form. Water vapor from the surrounding air creates frost on the surface of dry ice over time. The temperature at which carbon dioxide will sublimate is just about -80 degrees Celsius, much colder than the freezing point of water. Therefore, we are not only witnessing the sublimation of carbon dioxide, but the deposition of water. Deposition is the opposite process to sublimation. It is when a gas turns directly into a solid without passing through the liquid form. This occurs all the time in winter, when water vapor in the air turns into frost. Deposition of substances such as chromium, gold, platinum, copper, and other metals is frequently used in the semiconductor industry to create electric contacts, sensors, and other microscale or nanoscale electronics and optical devices. Ionization is the process by which a gas is converted into a plasma. As heat is added to the gas, the energy of the gas increases to such an extent that electrons orbiting the atom are ripped away, causing the gas molecules to have imbalance of electric charge. Recall from lecture 11 that an atom with different numbers of electrons from protons is known as an ion. De-ionization is the reverse process. It occurs when a plasma loses energy and gains the electrons back, converting back to a regular gas. A phase change diagram shows the relationship between temperature and heat in a substance. The x-axis of the graph shows how much heat is added to a substance. In our class, that heat will be measured in units of calories. Along the y-axis is the temperature of the substance, measured in units of degrees Celsius. From these graphs, we can learn a lot about a substance. We can determine latent heat of fusion, latent heat of vaporization, and specific heat capacity of the solid, liquid, and gaseous forms of the substance. The graph starts in the lower left corner on a rising slope, levels off, rises, levels, and then rises again. Each of the rising slope areas correspond to areas where the substance exists as a solid, liquid, or a gas. When heat is added, the temperature increases. The straight, horizontal line areas of the graph correspond to the transition between states, solid to liquid and liquid to gas. In these sections of the graph, heat is added to a substance, and instead of the temperature changing, the phase is changing. The latent heat of fusion can be determined by reading how many calories it takes to convert the substance from a solid to a liquid. The latent heat of vaporization can be determined by reading how many calories it takes to convert the substance from a liquid to a gas. The specific heat capacity is equal to the inverse of the slope in each of the rising slope areas. You can calculate the specific heat capacity of solid, liquid, or gas by dividing the number of calories it takes to heat the substance in that state of matter by the increase in temperature of the substance. This graph shows the relationship between heat and temperature for 1 gram of water. We can read from this graph that it takes 80 calories to convert 1 gram of water from solid ice to liquid water. That is the latent heat of fusion. The latent heat of vaporization is 540 calories per gram. The specific heat capacity of the solid form of water, ice, is the amount of heat, in this case 25 calories, divided by the increase in temperature, in this case 50 degrees Celsius. The specific heat capacity of ice is therefore 0.5 calories per gram degrees Celsius. It takes 100 calories of heat to change the temperature of liquid water by 100 degrees Celsius. The specific heat capacity of liquid water is therefore 1 calorie per gram degree Celsius. Thanks for taking the time to learn about phase change. Until next time, stay well.